got into this as a business about 2009. Started doing some projects for a chocolate factory where we recovered the waste heat from the cooling process rather than them burning coal, and that was very successful. And then we, fairly quickly after that, did what is still the world's largest 90-degree heat pump using a natural working fluid. And I'll say a good bit more about that as we go through. But essentially now this is a specific part of the Star refrigeration business. We decided to stop calling ourselves refrigeration when we're talking about heating and refer to it as Star Renewable Energy. I certainly found it quite confusing, so I don't know what other people thought. So this is a little bit about the part of the business that I and Nikki focus on, and how we kind of see it fitting. You've probably picked up, I've known most of the speakers that have spoken so far, and I've listened to them and basically been absorbing what they've been telling me for the last 5 or 6 years or so to come to the conclusion that it's really worth looking at devices which are cleaner and lower carbon. So that's why we're still very committed to this. I have to say it's been incredibly challenging. It's a very slow and stubborn market. Really quite staggering. And I've met the odd skeptic along the way, like Phil Jones, who's now... yeah, I'll tell you the story tonight when I first met him. Anyway, so large heat pumps, what do I mean by that, first of all? Well, there's kind of two parts of the family. There's the air source heat pumps and water source heat pumps. And in the case of air source heat pumps, they're about 400 kilowatts in capacity, and the one that we've built for a housing estate in Glasgow, where they're going to take electric heaters out of the properties and fit radiators, and we'll run the district heating at 62 degrees, is for about 400 kilowatts, as I said. And then there's the water source ones, which are the first thing we got into. And we've done several of these. We've done one that takes heat from a fjord. We've done one that takes heat from the cooling process in a dairy in the south of France. There's one that takes groundwater underneath Zurich. There's one that takes heat from the new harbour that they built for the Norwegian army. And the most recent one is taking heat from a solar farm where the heat is given to us at about 55 degrees and we boost it up to 80. I'm not going to say too much about that today. It's more about the water source ones. So here's a picture of Drammen. 6 very large heat pumps totaling 13.2 megawatts of heat capacity at 90 degrees. The source of heat being that fjord there, which despite the surface temperature obviously going quite cold, at depth at about 40 meters it stays around about 8 degrees all year round, which is very fortunate because that's not a bad temperature to start with as a heat pump. The key thing for this is the capacity that they're getting. This is a 28 megawatt facility, this building here, which is made up of 13 megawatts of heat pumps and 15 megawatts of gas boiler. And yet, the part that's 13 megawatts, so less than 50%, delivers around about 85% of the annual heat demand for the building. So it's the first place they go to for heat. There's a very simple reason for that. It's not because they're tree huggers. It's entirely down to the economics. They can make heat in Norway for about 1 pence per kilowatt hour. They've got a pretty good price for electricity, and as a large customer, they can burn biomass elsewhere in the network at about 3 pence, and they can burn gas at around about 5 pence. So 5 pence or 1 pence. So fairly obvious why they run the heat pump so much. And it's had a birthday. It has a birthday every day, as far as I'm concerned. And it's not 5 years old. And I tried Googling for 350 warming, and this is what I found. It's obviously not me, but it's had its 350 gigawatt hour birthday. And in fact, it's probably getting on for 400. So we stopped buying candles and cakes for it and just are very pleased that this plant has been delivering 85% of the heat from that facility for nearly 5 years. And it's essentially zero carbon already. So this question about Paul's fancy graph there, are way over to the left. It's principally hydroelectricity. They're getting their heat at zero carbon, basically, and that's fantastic for them. So a little bit of the basics of heat pumps and what they are. They are sometimes described as a big fridge in reverse, except it's not really in reverse. We're still moving the heat from the left side to the right. So I don't like the reverse bit, but it is essentially a big fridge. But basically, so long as we can cool something down, we can by taking heat out of it, we can move that through the system and it pops out the other side at a higher temperature. Now, what that temperature is very dependent on the design and what we're trying to do, but think of it as moving heat from the left of the screen to the right. We have to put some work into the system in the electricity, so the trick is to do the maximum amount of heat movement for the electricity. The air source heat pump is kind of similar, except it's air that's coming in. All I'll really say about air source heat pumps is consider the climate in the UK. We genuinely do get about 3 weeks of summer, 3 weeks of winter, and 46 weeks of sprotum. It's a fantastic climate for air source heat pumps because it's never terribly cold. You know, we don't go skiing and we don't have to de-ice our cars terribly often. So this whole thing about, oh, it's too cold for air source heat pumps, it's really not entirely true. There definitely have been some bad examples put in, but done correctly, and that's what we've done with this one is we've got a very good defrost system on it that's automatic, and basically we're seeing the temperature between 0 and 10 degrees much of the year. So not terribly exciting, but it's a good place for air source heat pumps. So what do we think of as large scale? Well, heat pumps, typically somebody, if they were saying large heat pump, they'd be meaning 50 to 100 kilowatts. That's clearly much smaller than what we're talking about. Actually, the capacity is really just down to how much heat you need and what the right size is. You don't want to make it too big because then it will be sitting not delivering. It's only saving money when it's running. And equally, we've got to think about the temperature very carefully. We can get to 90 degrees if it's large enough, but it probably doesn't make sense to go to 90 if you can go to 80. And I'll say a bit about that in a second. Currently with the air source heat pumps, we're kind of limited to about 62 degrees. We might get up to 65. If we use a natural working fluid, we could maybe get up to about 70. But again, the cooler temperature is better. So this is a housing estate that's going to work at district heating at 62 degrees. So really much, much better than what would be considered industry average. So let's look at a couple of systems to try and look at some of the factors that affect it. So this is for a 2 megawatt system, and we're heating from 55 to 75. I would contend that 55, 75 is broadly speaking going to displace a gas boiler that's been running at 82, 71. The reason for the 71 or 72, depending which way you take it, is to keep the flue temperature in the gas boiler high enough that there isn't condensation happening in the flue. But if we're not running the gas boiler, then we can use whatever temperature is enough to keep the building warm. So we'll go for 55, 75 and just look at some of the aspects. What's the source of heat? Well, we tend to see a lot of interest in rivers and the sea for the simple reason that there's lots of blue on that map and it keeps raining. Not quite at the moment, but probably will do at some point this week. Industry heat, we could recover heat from industry. Sewers, the guys from Shark are here and have done some fantastic projects where they're recovering heat from the sewers. There's some experts in the room about boreholes and groundwater. Or canals, there's some experts in the room about the canal network, it's extensive. Or groundwater being pumped out, cooled and put back again, so open source loops. Or my particular favourite, I have to admit, is rivers because there's so many of them in the UK and they're so big. That's a picture of Glasgow. And principally, when you think about it, most of our towns and cities exist next to rivers for a variety of historical reasons going back thousands of years to do with fishing and water and defence and transport and industry and so on. So the cities all tend to be on rivers. If they're not, guaranteed they're fairly close to large sources of water, be it sewage treatment plants or whatever. So the only thing to really consider is the heat pump doesn't care about the source of water, so long as it's following these sort of principles. How accessible is it? Clearly you don't want to use a source that's 2 kilometres away because that's going to be quite expensive. How big is it? Clearly you don't want to spend awful lot of money and go after a relatively slight source of heat. How cheap is it to get the heat from that source? How predictable is it? You know, can you say with absolute certainty that source of water will still be there? How safe is it? You know, are we talking about doing some groundworks that might be disturbing anything? How durable is it? And particularly over the course of the year, we certainly don't want to see something that's not viable just when we need it. So we're trying to get as durable. How warm is it? Quite clearly is important. I'll say a good bit more about that in a second. And how clean is it? So in terms of the way that we look at this, so this is our 55 to 75 network and the efficiency. And basically all to say in this slide is, the warmer it is, the less work the heat pump has to do. Think of it as moving heat uphill, but from a higher starting point. So clearly find something warmer is a good thing. Equally, with the network temperature, you can see a correlation between a warmer network not being as good. So if we can move the network temperature to the left we bring that in. The really key thing from these two graphs is a lot of the assumptions and predictions that have been made about heat pumps and their suitability has really been done on fairly poor heat pumps in all fairness, of efficiencies at 3. Now, if we can do an efficiency of 3 at 90 degrees in Norway, then surely we can do 55, 75 at better than 3. So I think we have to uprate some of our estimations of what we'll be doing. Just having a quick look at the cost of it, we live in a world where there's an incredible amount of incentive for it, but let's take a fairly tough example of electricity at 10 pence and a efficiency for the heat pump just over 3. So we'll be making heat for 3 pence. Equally, if we're buying electricity at the right time of day, we might find that the electricity is cheaper. There's an odd thing between electricity and gas. Gas is the same price every half hour of the day. Electricity is up and down. It's even negative at certain times of the day. We're paying wind farms not to produce electricity. Equally, if you bid on the market and say, I will switch my demand on, you can get a good price for electricity. So there's an aspect of that we might have a better situation. There's then the RHI, the Renewable Heat Incentive. It still exists. It's reckoned to be carrying on for at least another 5 years, and it pays 8.7 pence for the first 15% of the rated maximum output. So a 2 megawatt heat pump would pay the first 1,314 hours times 2,000 kilowatts at 8.7p, and then the remainder, and it's metered, it's not deemed, so the remainder at 2.6p. So at best, if we're getting electricity at the right time of day, and the first portion of the RHI, we're making heat for minus 6.6p. So if this is a commercial consideration, that's clearly a good place to be. Got to think about where we're getting the water from as well and what the costs are. Certainly up in Scotland, SEPA, the Scottish Environmental Protection Agency, have basically said they want to be not just the policemen for industry, but the supporters of progressive solutions. So we're seeing that they're making the system as easy as possible on these rivers. Now, quite clearly, there's easier bits of rivers and harder bits, so a prime salmon fishing part of the Tay is clearly going to be different from the middle bit of Glasgow. So thinking about where that is, but they're keeping the fees low. So, in summary, heat pumps do work above 50 degrees. There are lots of sources of heat. Network design affects the outcome. They do get better as the grid decarbonises. And to go back to this chart, we'll call it the Paul Woods chart just for clarity. We're in here at the moment, right now, about 355 grams. So we're definitely round about this bit here. And we do have to be very careful of what's happening, but my view is that if we do it, and it's not too bad at the moment, but everything is moving to the left, then fortunately we've picked something that gets better over the next 5 years, 10 years, or 15 years. So it's a good time to be thinking about that. What this graph doesn't show is two things. Firstly, that's still based on a COP of 3, which is a little bit miserly. And secondly, it doesn't say anything about the useful cooling that we could do. So if we situate a heat pump in the right place, we could be doing heating for some customers and cooling for others. So a university has always got cooling activities going on. So we should be thinking about joining up heating and cooling as well.